So my name is Frances Buckland Willis. I'm a postdoc at the LPENS in Paris, and I'm here to talk a little bit about some work I did in my PhD about the high and intermediate velocity cloud population in the Small Magellanic Cloud. So hopefully many of us are familiar with neutral hydrogen in the universe, but neutral hydrogen is a very important part of hydrogen, which is obviously an important part of the ISM. And in the neutral phase, typically what we see in local conditions in terms of temperature ranges is that it exists between about 50 to 8,000 Kelvin. So below this lower limit, we start to get into the molecular range of things. And above the upper limit, we start to get into collisional ionization. So even within the neutral hydrogen phase, we can further break it down into three main phases. So we talk about these three phases, the CNM, the UNM or the LNM, and the WNM, and these stand for the cold, unstable, lukewarm, and the warm neutral medium. So can you guys see? You can see the cursor, right? Okay. So these are typical ranges for local conditions. These are not prescriptive across the universe, but these are sort of the ranges that we look at. And we can define these sort of temperature ranges by looking at the phase diagram of the H1. So these are some figures from the Wolfeye paper in 1995, where they explore the variation of the H1 phase diagram under a lot of different ISM conditions. But the basic principle here is that when we balance all the heating and cooling processes for the H1 in the ISM, we get this characteristic phase diagram. So in terms of heating processes, our dominant process is photoelectric heating at all densities, but the cooling is dominated by different processes at different densities. And so this can really affect the shape of the H1 phase diagram. And it gives us this characteristic little wiggle here. So I've highlighted in red, green, and blue the different phases of the H1 that we're concerned with. So in the low density regime, we're in our warm neutral medium phase. Where the gradient becomes negative, we're in our unstable or lukewarm neutral medium. And then at high densities, we become stable again in our cold neutral medium. And so the consequence of this little wiggle and this unstable phase is that also at certain pressures, depending on your conditions, you can have CNM and WNM coexist in a stable phase, right? So the delta Y here determines this pressure window that this can occur over. So when we observe the neutral hydrogen, we can observe it like any spectral line in emission or in absorption. And to observe the H1 in absorption, we need background sources. So we typically use radio continuum sources, whereas for emission spectra, we can observe it wherever there is neutral hydrogen, which is pretty much everywhere. But the absorption spectra, even though we have less coverage because of this background source density limit, we are sensitive, typically when we do the observations, sensitive to smaller scales because we have smaller beams. And we are also sensitive more to the CNM because the CNM has the highest optical depth, it's the densest gas, and so we see it really well in this absorption spectrum. Whereas in emission spectrum, we have a combination of all the signals from the H1. So it's very easy for the narrow CNM signals to get drowned out. But we need both these measurements really to fully encapsulate the two-phase medium, but absorption measurements are few and far between. So in this work, what I focused on is using data from the GASCAP survey. So this is a galactic ASCAP survey. Hopefully some of you are familiar with the ASCAP telescope. It's one of the precursors to the SKA in the mid-frequency range. So our survey is covering the galactic plane and the Magellanic Clouds, and we started the pilot observations in 2019. And the Small Magellanic Cloud was the first field to be observed. So the observation that I'll present today is a 20-hour observation, but we will have a full 200 hours of observation, which is going to increase our sensitivity by a factor of 3. So we hope that this survey is going to, well, we know that this survey will improve upon the resolution and sensitivity, but we're hoping it's going to allow for really good comparison with sub-millimeter infrared millimeter traces. So this is just a comparison for the Small Magellanic Cloud. If you want to compare for yourself and go to our wiki page for our collaboration, the QR code will take you there. But this was now 25 years ago. This data was taken at 98 arcsecond resolution. And this is our integrated, or maybe it's peak intensity, image here, compared with the same image for our current survey data. So we can see a lot more small scale structure coming through here and a lot of higher information. And we get a lot of information about the periphery as well. We can see that the bounds are extended there. And this is just a map of our absorption measurements from this survey. So this is what I was saying about the source density. that we have this coverage, and we can have some measurements of the CNM through absorption. These squares show where we have detections, the circles where we have non-detections, and the triangles where we have too much noise. So we will, in subsequent surveys, as we increase our sensitivity, we will get more sources and we can make more measurements of the CNM through absorption, but there's always going to be this intrinsic limit. So the idea from this work was to try and use emission data to get an estimate on all the phases of the H1. So in the commissioning data from ASCAP, so before we started our GasCap survey, while the antennas were not all online, there was data taken of the SMC, and they discovered these small scale structures at considerable deviation velocities from the rest of the galaxy. So these features were relatively compact, and they showed strong gradients over a few tens of kilometers per second. So in their work, they weren't able to analyze the H1 spectra because of the spectral resolution. But in my work, we wanted to know if the structures are cold, warm, or something in between. So this is a column density map of the SMC in grayscale. And then in color, I've shown the column densities of these structures. But you can't see them very well on the total column density map because we're summing over the entire velocity spectrum, so they do get washed out a little bit. But you can see that they all reside in the north of our galaxy here. So the question is then, how do we characterize these clouds? So Gaussian decomposition is a very straightforward way that we often use in spectral lines, especially in H1. And so it's a very simple idea. Basically, you model the spectrum as the sum of Gaussian components that have some centroid velocity, which represents the bulk velocity of the gas, some dispersion, which is the broadening due to the velocity of the gas within. And this is broadened by both the kinetic motions from the temperature of the gas and turbulent motions of the gas. And then your amplitude is some intensity, and you can get a column density in combination with that. So we take this noisy spectra, we model it as a sum of Gaussians, and we take our noisy spectra to a cleaner model. So it can also be a useful way of denoising your data as well. So Isabel mentioned this in her talk before, the ROSA algorithm. So we use this in this work as well. It was originally designed with H1 data in mind, but in theory, you can apply it to any data you want. And it forces spatial regularization in its fitting regime. So I won't go into the details, but you're welcome to ask questions if you want later. But basically what it allows us to do is create maps of the different phases across the entire field of view that we're fitting. So I used this algorithm on each of the clouds, and we obtained average properties as well as maps across the fields. And we basically use this maximum kinetic temperature. So if we assume that all of the broadening is due to the kinetic motions coming from the temperature of the gas, then we can define an upper limit on the temperature of the gas to classify it roughly into the three phases of the H1. So for each of our clouds, we have here is the alpha cloud, here is the cloud, and here is the gamma cloud. For the gamma cloud, we find that we have two CNM components and then one WNM component. And this is just an example of one of the fits to the spectra in one of the denser parts of the cloud. So you can see two narrow components and one wide component. For the other two clouds, they both have a CNM component. They both have an unrelated component, so at a different velocity, very wide diffuse emission. And they both have either a WNM or a UNM component as well. And so this is just an example of what these solution maps look like. So we can create column density here on the left, velocity in the center, and then on the right, the velocity dispersion. So then we can look at each phase of the cloud, and we can see how the velocity trends look between the phases and what the column density looks like. So in this cloud, we see that the CNM appears to be enveloped by a less dense WNM. We have this little cavity on the western side that has been previously catalogued as an H1 shell in shell studies of this galaxy. And we find that there's a strong velocity gradient in the CNM, which is aligned with the direction of this cloud from the main body of the galaxy, but we don't see the same velocity gradient in the WNM. For the Hook cloud, we don't really see a strong velocity gradient north to south. This is 2 times larger, well, 4 times larger, but 2 in each axis than the previous cloud. But we don't see anywhere near the velocity gradient we see in the other one. We do see that the CNM is enveloped by the UNM in this loop, but the central area of the loop is completely void of any H1, really. And we don't see the C and M come down on this eastern side either. But we do know that both phases from this decomposition follow each other well in velocity. For the gamma cloud, it's a very different story. We have quite a strong gradient in both phases that moves south to north along the cloud length, and the cloud is elongated in the direction away from the galaxy as well. We know that the C&M and the W&M from this decomposition overlap in the center of the cloud, and the W&M envelope only exists at the north of the cloud, furthest from the main body of the galaxy. So we have this quite extended head-tail morphology. If we want to look at C&M fraction, this is just the column density of the C&M divided by the total column density. We can see that for the alpha and the gamma cloud, we have C&M fractions close to 100% when they approach the galaxy at the closest point, and they seem to decrease as we get further away from the galaxy. Whereas for the Hook cloud, the C&M fraction is enhanced only on this western side, and it only gets up to about 50%. If we want to look a little bit more closely at how the phases relate to each other, we can do some version of a PV diagram. It's not exactly a PV diagram, but we take a path through the cloud, and then we have our velocity on the y-axis of each phase. So the blue is the C&M and the red is the W&M, and then we have the difference between them at the bottom. So for these two clouds, the alpha and the gamma cloud, we seem to see some offset as we approach the galaxy between the C&M and W&M. It seems that the W&M is traveling a little bit faster. And we see this most extremely at the base of the alpha cloud, where we get towards this high density component towards the galaxy. So this is where we see an offset of about 3 to 5 kilometers per second between the phases above the uncertainty level. But for the gamma cloud, the uncertainties are larger, and I didn't detail here how we got the uncertainties, but feel free to ask later. And so we don't really have a conclusive offset here, but at some points it seems to be at about the same 3 to 5 kilometers per second. But for the Hook cloud, we don't see any offset between the phases. So if we want to have a look at other traces, we do have some measurements of the CO 2-to-1 line. These were taken in response to the initial discovery of these clouds in 2018. And we see for the alpha cloud that we have, out of the 8 clumps that were detected in the field, 4 of them align very well with our C&M velocities that we derived from the Rosa fits within a few channels, a few kilometers per second. We see that there's this unrelated group in the blue, and that doesn't really align with any H1. So that's a little bit of a mystery that we haven't solved yet. But for the Hook cloud, we only have it at the base of the cloud, and we have a lot of these very strong, because the size of the circle corresponds to the flux of the clump. So most of the strong sources align very well with our derived velocities for both the C&M and the W&M in this cloud, because they're well coupled. But unfortunately, we don't have any information for the other cloud. So if we want to try and measure some sort of density as well, we want to get an estimate on the density. We treated all the clouds as filaments. We defined a path through the cloud and took profiles perpendicular to the path using the RADFIL package. And it allows you to basically fit an average Gaussian where you can get some characteristic width. And we make the assumption that the filaments are as deep as they are wide, because we don't have any depth information from the H1 spectra. And we get physical widths ranging from 20 to 33 parsecs. So our beam here is 30 arcsecond. At the distance of the SMC, that's 9 parsecs. So this is a few beams, and this gives us number densities ranging from 1 to 5 per centimeter cubed, which is at the lower end that we would expect for C&M. So we think that we're not resolving fully the C&M here spatially, and so these number densities are definitely lower limits. So then we finally have to think a little bit about what could have formed these clouds. So we have some information from the different phases as to how they relate to each other, but can this tell us anything about the formation? It's very difficult to distinguish just from this sort of analysis an infalling cloud from an outflowing cloud, because we would see in both cases a cold head and a warm tail, which is very characteristic of what we see in this cloud in particular. But either if they're infalling or outflowing, they do both seem, these two clouds, to be affected in the direction of the galaxy. So there is more offset between the phases as we approach the galaxy. There is also some H-alpha emission at the base of both clouds, but we haven't been able to relate it dynamically to the clouds themselves because we don't have that spectral information. For this cloud, it seems much more likely that this is a stellar expansion case, it's very reminiscent. The scale of this is hundreds of parsecs, about 500 parsecs. It's very reminiscent of H1 chimneys that we see in the Milky Way. And so if we do some calculations, assuming some expansion velocity, because we don't really see the walls of this cavity here, we have to assume something, but we get, on the order of tens of stars, tens of mega years ago, would be the explanation and the energy required to expand the shell out to where it is. So in terms of future prospects, we all know that the SK is coming up in the next 5 years, which is very exciting. We're going to get improved spatial resolution, and this will allow us to go sub-parsec at the distance of the SMC. So we definitely hope to do follow-ups with the better resolution, and hopefully, because we know that the C&M filaments are on the scales of 0.1 parsecs from our studies of the Milky Way, we'd really like to see if that's the case as well in the SMC, because we don't really think we're resolving our structures completely here. And so this is an example of one of a high velocity cloud in complex C. In red is the C&M, and so you can see these very, very thin structures that we hope to try and see as well in the SMC in the future. And we're also going to get an increase in absorption source density, so we'll get a better picture of the C&M through that as well. Okay, that's it.